so we can go ahead and begin here. There was a request to go back to Dijkstra's and develop an algorithm, which is not in the book, so we'll go ahead and develop it here, of recreating these paths. So for example, given I over here, how do you recreate the path that you took to get to the shortest distance path from E to D over to G and then to I, right? If in fact that's the path we took, and I believe that it is. Right? So all you have to do is make sure that from the main algorithm that you keep track of all these triples, because encoded in these triples is the predecessor vertex that got you there, right? So for example, I'll just go ahead and highlight these here. How do you get to I? Right? So how did I get to I? You look at this triple over here, and you see that you came from G, all right? So that means that we're going to add G to this list over here, backwards, right? Because we're going from the destination vertex back to the original source vertex. Now, all we have to do is look up G here. How did you get to G? Well, you got there by going to D first at a total cost of 15. So you can actually rebuild the total cost as you're going along here. In fact, let's do that. The total cost here, in fact, it's just one number, 20. Whatever the path here is, it's going to end up costing me 20. And we can look at that and see that 5, 10, 5, indeed it was 20. Right? And that's encoded right here. So how did we get to G? We went to D first. So put in D, and then you went over to G. And then you ask another question of, well, how did you get to D? Well, you came from E. At that point, you have reached your original source vertex, and you've recreated this path. All you have to do is work backwards from the destination back to the original. So if we want to, we can write some pseudocode to codify this. Right? What's my input going to be? It's going to be triples from Dijkstra's and a destination vertex. I'll just call it a Y, right? Implicitly here, Dijkstra's, you started at a source vertex. So if you want to, we can say the source vertex as part of the input too. But that may not be necessarily apparent from the triples if you have a disconnected graph, but you can come back to this and see that this is the only one with that special flag value indicating that that's where you started. So it all depends on your encoding of these triples. You can probably just get that information directly from this output right here. Okay? So that's my input, and my output will be the path, given by Dijkstra, so the shortest weighted path from S to Y. Right? And then, of course, you would repeat this over and over again if you wanted to for each potential destination vertex. Now, if your destination vertex here was, this is an edge case that I won't take care of in the pseudocode, but if you can look at the weight here, and if the weight of that triple is infinite, you can immediately stop and say that there is no path, right? For example, going to J and H, there are no paths from E to either H or J, and so you can look at this weight right here and say, nope, sorry, done. Right? Immediately return with no path. Otherwise, what you're going to do is you're going to set up a basic while loop. Right? I'm going to set up a current vertex, and I will start at the endpoint, Y. While the current vertex is not equal to my source vertex, then I will start backtracking, okay? So this is going to be, I'm going to go ahead and have a triple here. I'll need maybe A, B, and then W for the weight. This will be the triple with this first one. I got to Y. How did I get there? I don't know, or not Y, but the current vertex, sorry. The current vertex. How did I get there? The predecessor, and then the weight. So all you have to do is go through this and find the triple here where that first vertex is equal to the current vertex. And how do you do that? Well, that's just a for loop, or it really depends. If it's a set in Python or something, you can go ahead and grab it, right? because once you have an equality in the first component here of a triple or of a tuple, it says this is it, right? Okay, so A, B, and W, I've got those. Right? And how did I get to A, or how did I get to the current vertex here? Well, you came from B. So I'm going to set myself up for the next time here and set current equal to B. But I also want to build my path. Right? So where do we start out with the path? The path will simply be Y, because that's the destination. And now my path will be the original path, but then we'll append, or prepend, excuse me, B to it. So do you see this? Let me annotate this. I will prepend B, the previous vertex, to the start of your path. All right? And then this last one just sets you up for the next iteration of this while loop. We might need to, at the end here, return or set this up so that P is going to be equal to S plus P, and then return or output P. Right? It's just a simple while loop, and you backtrack. Right? Questions on that? And again, why do we need to do this outside? Because we broke when the current was... actually, do we need to do that? I don't think we do. Let's see. Current will end up being this. And so, yes, we do need to do this. Yeah. Because it won't be done in the while loop. Yeah, go ahead.
So why do we prepend? So why do we start from Y, not from the source S? I guess?
Well, then you would be repeating Dijkstra's algorithm. We're recomputing the path, right? So I, what is the optimal path from E to I? The only information that we kept track of over here was the predecessor vertex. How did you get there? I came there from G. How did you get to G? I came there from D. How did you get from D? I came there from E. And that allows me to rebuild the path. If you want to modify Dijkstra's algorithm so that you keep track of the entire path instead of just the predecessor, you can do that. Right? And it probably won't be any computationally more expensive than just simply keeping track of the predecessor. Right? You just need to be careful, because if you find a better path, I got to this vertex here at a weight of 20. But now, because I've added this vertex over here, I can now get to this vertex at a weight of 5, right? That means that the entire path that I pre-computed to get to this vertex now needs to include now needs to be switched to this path that I got to this vertex, then to this vertex. Right? But if you keep track of a minimum amount of information here, I mean that's a little bit clear. I mean, if I were doing this, then I would keep track of just the bare essentials and then rebuild it like this. Okay. Let me make sure that we are online. Yeah, we're good. All right. So, as we were talking about yesterday, there's an alternative here called the Floyd-Warshall algorithm. The Floyd-Warshall algorithm, it computes all pairs' shortest paths. Right? It produces a path/distance for all pairs rather than just a single source. So in other words, you only need to run it once. It's more complex, of course, because you're computing all pairs' shortest paths, and we'll talk about the complexity here in a moment after we've looked at the algorithm. But otherwise, it gives you all the answers all up front. All right? It does so by keeping track of two matrices. It keeps track of two matrices. Right? So it keeps track of the minimum weight so far and a successor matrix. Right? So in this case, where Dijkstra's, the information that we kept track of, we had to build the path by going backwards. Here, we're keeping track of a successor. If I start at this vertex, which one do I go to next? Which one? So we're going to rebuild the paths by going forward instead. All right, so here's the idea. Well, first of all, let's go ahead and take I want a before. Yeah, there we go. All right, and let's just take a look at this this graph really quick here, right here. Right. So to start out with, I'm going to start out with a weighted adjacency matrix. Since this is a directed graph, it's not a DAG because it has cycles. But since this is a directed graph, it will not have a symmetric adjacency matrix. So let's look at what this adjacency matrix kind of looks like. A, B, C, D, E. A, B, C, D, E. And instead of a 0, 1 Boolean matrix where false means that there's no edge and true means that there is an edge, we're actually going to keep track of the weights in this thing. So for example, from A, I can go to B at a weight of 1. I'll put 1 in that entry. From A, I can go to C with a weight of 2. From A, I can't go anywhere else. So as far as the adjacency matrix goes, what entries should I put in here? What about 0? What does that imply? It implies that there's no edge, but really, what am I keeping track of here? I'm keeping track of the cost of traversing this graph. So can I go from A to E at a cost of 0? Nope, that would be having an edge here, but then its weight is 0. That's not what this is. So what is a flag value here that will indicate that you can't do that, or that it will cost you a lot? It'll cost you everything. It'll cost you an infinite amount. Right? You can't do that. Infinite amount, infinite amount. From B, I can go to E at a cost of 2. From B, I can go to D at a cost of 8. And that is all, right? So infinite, infinite, infinite. Yeah, go ahead.
Why is the A to A loop?
Oh,
A to A?
sorry, that should have been A to B. Thank you. 1. Oh, no, but you raise a good point. What if I'm at A? What's the cost of going to A if I'm already there? 0. So there is where you put in a 0. Right? C, I can go over to D, but that's the only thing. And so, but if I'm at C, I can remain there at a cost of 0. D, I can go to B at a cost of 4. D stays at 0, and is that the only thing? Yep. Infinite, infinite, infinite. E, I can go to D, but that's the only thing. 0, infinite, infinite, infinite. There we go. So that's where we start out with. We start out with the weighted adjacency matrix. Okay? Now, let's consider this graph. Can I get from A to E in this graph? Not directly, not without what? Not without going to B first. Is that the only possible path to get to E? I could go from A to C to D, then over to B, and then over to E. Right? So what I need to do is I need to think generically and inductively about this. So suppose that I've got two vertices, V sub I and V sub J. Right? Now, suppose that I found a path somewhere in the graph of a certain weight. And I will label that as W sub I, W sub J. Okay? Now, that could be infinite. As I have started out with A to E here, well, you can't get there. But now what if this would end up being infinite if I plugged in A and E for these two values. But now let's think about going to another vertex. And again, let's keep it general, let's keep it inductive. What if I considered VK as an intermediate point? Okay? In other words, I'm going to go from VI to VK somehow. And then once I stop there, I continue my journey over to V sub I. Using the same notation here, W sub IK and W sub KJ, those will be the weights of those two intermediate paths. If you went to this, if you followed the path that you found from this vertex down to this vertex, and then continued onto this vertex, it would cost you a weight of W sub IK plus a weight of W sub KJ. So in total, this is going to end up being a weight of IK plus wkj. Right? You have two options now. You can take this path, which might be infinite. In other words, you can't do it. Or you could take this path, which will have this weight right here. And again, one of these could be infinite, right? You can't go from this vertex to this vertex. But you can compare infinite to finite and say that, well, finite's going to be better. But not only that, but if this is finite and this is finite, which one do you choose? If you want to minimize the distance, the lesser. You take the minimum of w sub I j and w sub I k plus wkj. And again, if you can break ties arbitrarily, if both of these are infinite, for example, you don't update it. Right? If you want to stick with what you found so far, then do so. If you want to always prefer the new one, if it's a tie, that is. Of course, if they are not equal, then you have to choose the minimum in order to minimize the distance. Okay? This suggests an algorithm, right? For each pair of vertices, consider every other vertex as an intermediate vertex, and then compute the weight that you've seen so far, compute the weight of using this vertex as an intermediate vertex, and then choose the best one. And update your matrix. If you find a better one, then update that entry. Okay? So that suggests the following algorithm. Oops. Where am I? There we go. All right, let's go ahead and, well, here, I'm going to put in a new page here. Blank. All right. And here's Floyd's algorithm. Floyd's. It's called Floyd-Warshall. I think Warshall's algorithm, it does this exact same thing, but only for transitive closures. So in other words, it does it for Boolean. That you can go from A to B, or you can go from A to C and C to B. Therefore, you update the logic. It uses the same exact algorithm here, but instead of weights, you're using Boolean values, true and false. Okay. So my input, of course, will be a weighted graph G equals V comma E. Right? And my output is just going to be the distance matrix. My output is going to be a shortest distance matrix D and a successor matrix S. Okay? We'll talk about how that gets updated here. So initially, D is going to be an n by n matrix, with initial values of for I and j equals 1 up to n. Right? When I write that, I am iterating over all pairs. Right? So think about 2 for loops, basically. Okay? And the entries are going to be the weights of vi, vj. That could be infinite. Okay? And s sub ij is going to end up being initialized here to j for all edges. V sub I, V sub j in the edge set. It's going to be nil otherwise. So for example here, we're jumping ahead a couple of iterations of this algorithm, but when I say nil, I mean this. Right? There is no successor because the weight is going to end up being infinite. Right? Okay? That's just the initialization. Now all we need to do is, like I said, where is it? For each pair of vertices, consider for all other vertices as an intermediate value, or as an intermediate vertex. So for I running from 1 up to n, for j running from 1 up to n, right? This is, and again, annotation here, this is for each pair of vertices. consider for k running from 1 up to n. And this is the intermediate vertex. As depicted in this picture right here. This intermediate vertex right here. That's why I used I, j, and k. Okay? So 3 for loops. Predict right now, and I'm not doing any more for loops nested in this. Predict right now, what's the complexity of this thing going to be? N cubed, exactly. Right? I mean, it's so, like you were saying, taking the test and saying it's so obvious we don't need to do it. I'm going to say it's so obvious we don't need to do it. Right? All right, so all we need to do is update the distance here. D sub ij will end up being the minimum of d sub ij. If you've already found something, then go ahead and stick with it. Otherwise, d sub ik, go from vertex I to vertex k, and then go from vertex k to vertex j. Right? And you take the minimum between those two and update the distance. Okay? You also need to update the successor matrix. If, and I'm run out of room here, if d sub ij changes, update. If it doesn't change, then don't update. But update s sub ij to be s sub ik. And we'll understand that here when we look at the successor matrix and rebuild our paths. All right? So questions on that so far? Otherwise, it's a very simple 3 nested for loops and 2 conditions. All right? Now, obviously, I'm using math here. The minimum of this and this, you would use a if else, right? Yeah, and with a comparison. Right? If d sub ij is strictly less than d sub ik plus whatever, then you do one thing. Otherwise, you do the other. Okay? All right. In fact, I don't think you would need to use an else because the else's do nothing. So it's just one if statement. Let's take a look at an example run. Now, what I've done to make this interesting is I've jumped ahead 2 iterations. We did it for k being 1 and k being 2. Now, implicitly here, when I say k is equal to 1, I mean we considered A as our intermediate. We considered vertices v sub I, v sub k, and then we went to A first. And then A over to whatever. Right? Now, is A going to be, on the first iteration, you can imagine that that won't really lead to any updates, right? Because A is a universal source. So A cannot be an intermediate vertex for anything, because you can't get to A. From A, you can get to anything else, but you can't get to A to use it as an intermediate vertex. So this is why I've jumped ahead a couple of iterations. Let's go ahead and go with the next iteration here, where K is 3. In other words, our vertex is C. Right? Is C going to be an intermediate vertex for anything? Just by looking at the graph? Sure. You can go from A to C and then over to D and improve your chances. Previous to this, and let me go ahead and annotate these. This is A, B, C, D, and E. Right? Now, previous to this, could I get to D from A already? Yes. At what cost? 9. So in other words, D sub, and here I'll substitute the values here. D sub A, D. Right? In other words, D sub 1, 4 is equal to 9. Right? But now I'm asking whether or not if I use C as an intermediate vertex, can I do better? This is basically asking D sub 1, 3 plus D sub 3, 4. Right? Is that better than this up here? Well, all we have to do is look it up. I can go from 1 to C at a cost of 2. I can go from 3 to 4, in other words, D to E, or no, sorry, that's C to D, right? Let me annotate these. This is D sub A, C, plus D sub C, D, right? And it's also, I mean, it's the same thing. I'm just mapping letters to numbers for the indices, right? All right, so C to D. C to D at a cost of 5. So plus 5 plus 5. Now, look at this from the perspective of the graph. You're going from 2 to 5. The total is 7. Is 7 better than 9? In other words, is this path right here better than the path that you found by using B as an intermediate vertex to go down to D? Yes. So what do? We update. Come on. Nope. We update, what was it, A to D to B, what? 7. Right? And that gets updated. Are there any more? Yeah, there's more. Well, I mean, there are going to be other things. For example, if you use C as an intermediate vertex, now you can go from A to C to D to B. So A to B, but you can already get from A to B at a cost of 1, so that's not getting updated. Otherwise, you would have to have, and you haven't considered D yet, by the way, either. You're only considering C as the intermediate vertex. Okay? Now, what gets updated here as far as the successor matrix goes? Since we did update this, then we update the successor, as we wrote right here, forward, sorry. It changes from Sij to Sik. So S sub 1, 4 gets updated to S sub I, K, which in this case is going to be S sub 1, C, right? Or 1, come on. 1, 3, which is equal to S sub A, C. Right? Now why? Because the successor, how do you get from A to D? You first go there by going to C. And how do you get to C? Well, if you start at C, you're there, you're done. Right? Now let me jump all the way forward into the future and look at the successor matrix. So after I'm done with Floyd's algorithm, this is the successor matrix that ends up from that run on this graph. How does that tell us how to build the path? For example, what? 7. Yeah, here we go. How do I go from A to D? What's the optimal, that is the least weighted path to go from A to D? If you just look at this graph, you might guess, oh, okay, well, I can go from A to B and then over to D. That's a cost of 9. Can I do better? Remember what I just showed you. You can do it by going better to 2 and then 5, 7. Can you do it even better? How? A to B to E and then backtrack to D. In other words, the longest path in terms of the number of edges is actually the shortest weighted path. How can I get that from just this matrix right here? I'm going to ask, what is the successor of going from A to D? Going from A to D, where do you go first? B. Right? So I know that in my path, I go to B first. So A to B. Now where do I go? Where do I want to go again? D. And this is my question mark here. How do I get over there? Well, I went to B first, and so the question has now changed. How do you go from B to D? S of B to D is equal to, and then you look that up. B to D tells me to go to E next. Right? And now I update this. How do I go from E to D? E to D means you just go to D. And so this transforms into a path by looking at all these successor matrices. And guess what? It's the exact same algorithm as this one, but in reverse. You're doing a successor instead of a predecessor. Right? Do we need the pseudocode for that?
That'd be nice.
Okay. There we go. all clean. I think I've got it. Yeah, here we go. So construct a path, shortest path, from Floyd's. Don't name your function this. I barely want to name my pseudocode this, right? But that is what it is, right? All right, my input is going to be a successor matrix S from Floyd-Warshall, and and two vertices. Say V1, VI to VJ. So of course you could repeat this for all pairs very easily. This is just a subroutine. My output will be the shortest path, P, going from VI to VJ. All right. All I need to do is start at V sub I. And again, note here that I'm using I'm going to be using the same notation that I did here, to build a path, I'm just using concatenation here. If you were to actually do this in Python, then you would append it or prepend it. There's no prepend in Python lists. What is it instead? You append and pop from the end, but on the front, insert, and then you give it the index, insert at 0, right? Okay, something like that. Anyway, I'll start with my path at V sub I. X will be my current vertex. And where do I start that? Also at VI. And so this is my current vertex. X is the current vertex. And then while you have not hit the end, while your current vertex is not equal to V sub j, your destination, right? Remember that V sub I is your source. That's where I'm starting. V sub j is your destination. So once I hit my destination, I break out of this while loop. I update my current vertex based on the successor matrix from X over to V sub j. Right? And then I update my path by appending X to it.
Wait, which one is V sub j?
That's the destination.
No, I mean like up front you define V sub I twice,
So
but there's no
this
V
is
sub j.
the index
Oh wait, that's an input.
of, yeah, this is a
Sorry.
subscript here. Index of V sub j, which I guess you could just say is j. Right. If I were doing this, I would actually use like the actual nodes instead of indices. Well, in your assignment, the nodes are indices to make your lives easier, right? And I'll output P here. And that's it. So what is the complexity of this one right here? For just one pair. It's linear, right? Linear with respect to n, because can you go, what would happen if you went more than n minus 1 edges? Yeah, you'd be going over multiple edges multiple times. Right? Well, maybe that's not so bad. What if I have a graph that looks like this? -1, -1, -1, A, B, C. Negative values. What is the length of the shortest path from A to C? Yep, there is no lower bound on it. Right? You see that? You can go all the way around this as many times as you want and find an even shorter path, shorter weighted path, I should say. Right? So Floyd-Warshall's does not give you an answer when you have a negatively weighted cycle. Negative values aren't necessarily a problem unless you have a negatively weighted cycle. And then you get into this. And it doesn't work because the problem is ill-defined. There is no shortest distance path, right, by definition. So you could potentially, you know, detect this. How?
By checking to see if the weight is less than 0.
The weight could still be less than 0 and you wouldn't have a problem. For example, here's another example. -1, -1, but then this is 2. Is there a negatively weighted cycle? Nope. So it doesn't buy me anything to go around this infinite. It's always going to be 0. In fact, if I bump this up to 3, you can see that it actually costs you to go around in a circle as many times as you want, right? So negative values aren't necessarily bad. You can have a negatively weighted path, just as so long as you don't have a negatively weighted cycle. How could you detect such a thing? So maybe some of you have seen what's called a Markov chain. A negative weight is still okay.
Oh wait, from one point to itself, so one diagonal?
Okay, there you go. Or you could go one more iteration on this, and if it doesn't change, you know that that's the best you can do, right? But if it does change and something goes down, that means that you can go do it again. You can do it n more times and it'll go down again. Do it n more times and it'll go down again, right? So if it's not a stable matrix, basically, I don't know if you've ever seen Markov chains, and you know that if you take this matrix here, A, and you raise it to the n, right? If that's equal to A to the n plus 1, if in other words, if it didn't make any changes, right? And this is not matrix power. This is matrix. Is it? No, I mean using this criteria, I should say. Sorry, it's not matrix power. It's using this criteria right here, and applying it n times. If you apply it one more time and it changes, then you know that you have a negatively weighted cycle. Right? In fact, I think it will work if you just take the powers of the adjacency matrix, the weighted adjacency matrix. If you take the power and the power and the power and the power up to n, right, that will get you. No, now I'm thinking that that's the number of paths, the number of non-simple paths. I forget, there's a trick to it, but if you just take matrix powers, you can get some answers out of that on whether or not it's stable. It's kind of like a Markov chain, right? A probability transition matrix, and what you do is you take it and you do a matrix power, matrix power, matrix power, and eventually if it converges and stabilizes, then you've got a stable Markov chain. But if it's all going all over the place every time you do this, then it's unstable, right? Something like that. Question?
We have to deal with that on our homework if we decide to go with a Floyd-Warshall algorithm or no?
Well, I mean, if you implement Floyd-Warshalls, you'll definitely have to implement something like this, because you do need. I don't want to see the adjacency matrix. I don't want to see the weighted successor matrix. I want to see the paths. Right?
Right.
So if you do Floyd-Warshall, then you got to do this. If you do Dijkstra's, then you got to do this.
Okay,
Right.
and if we do the Floyd-Warshalls, and then you have to do like the thing you showed before, you know, do we have to account for negatively weighted loops or whatever?
I don't think we did that to you on any of them, but there's nothing to prevent you from doing that to everybody else. Right? Here's a nice test case to throw into your stuff. Well, this one right here. Right? Submit that as your test case. Again, you only have to pass the official test cases. I used to encourage people to have corner test cases or edge test cases that would break other people's code, and some people have come up with some really cool ones, like, you know, something that would exploit IEEE floating point numbers if they chose to use a float instead of a double or something like that. And then they would get completely wrong answers because they should have used a double.
That's easiest.
Yeah, it's good. I like it. That's how you test software, is you intentionally try to break stuff, right? There's also something called chaos testing, where or it's basically a load testing, but you try to, or fuzzing, right? You try to give bad inputs to a program and see if you can break it or if it's resilient. Chaos testing, you try to simulate, I think it comes from Netflix. You simulate a server crash and see if people's shows are, go over to the fail-safe server or something like that. Or too many people watching Dune all at once. Can we still service the bandwidth to everybody, right? That's load testing, right? So you try to break things all the time with testing. That was the last of the graph algorithms that I was going to cover. Graphs will, of course, come up throughout your entire lives because everything is a graph, because everything is a relationship between entities, right? Chemistry is a graph. Language is a graph. If you diagram a sentence, everything is a graph. Right? No question? Yeah, go ahead.
So we said that doing Dijkstra's algorithm was n log n, correct?
E log v, so m log n, but you can say that it's n squared log n because, or sorry, Dijkstra's, or are you talking about minimum spanning tree or Dijkstra's?
So I'm wondering if would a repeated application of Dijkstra's be more efficient than?
Good point. So this one, and from the perspective of your assignment, it's not going to matter. We don't have big graphs there. But again, like as you observe, this is going to be n cubed, right? Building a path is going to be linear, and since you have to do it for all pairs, it's going to end up being building a path n squared, n cubed. So these two are equal. So they're at most it's going to be n cubed. But now Dijkstra's. Dijkstra's is order E if you use an optimal heap, or you can get it down a little bit further if you use a binary heap, but that's going way too far in my opinion. But if you do, say, a heap on the vertices, it's going to look something like this, which is equal to order m log n, which at most is going to be order n squared log n. So from that perspective, one run is better than one run of Floyd's, but Floyd's gives you more information. And as you observe, if you have to do this n times for each vertex, then it becomes order, n cubed log n. So yes, it is worse technically to do Dijkstra's over and over again, but it ain't that much worse.
But you said Dijkstra's gives you more information or less?
Dijkstra's only gives you a single source. Floyd's gives you all the sources. That's why you only have to run Floyd's once, but Dijkstra's, you have to run it n times. Potentially. All right. So what do we have for the rest of the semester? We have like 2 weeks before the break. I think that we can probably cover dynamic programming fully in that time. And if we do, we could potentially take that Monday off from the break week, right? And so we would have a full week off. After that, after we come back, we'll do computation, computability, which are things like NP, P and NP, whether or not some, computational models like finite automata, Turing machines, whether or not even, are there problems that are even computable at all? It doesn't matter if they're efficient, like they're linear or they're quadratic or anything. Is there an algorithm to solve it at all? And there are things that are of practical interest where you can demonstratively prove that it's not possible to solve them, that there is no computer program that would allow you to solve this for all inputs, for all infinity, right? And it gets into, meta mathematics is what you would call it, I guess, where well, not even that. Like axiomatic set theory, you've seen that before. When you looked at sets, did you talk about Pinot or ZFC, Zermelo-Frankel? No? Okay. The simplest form I'll give you to think about is the liar's paradox. Right? The simple sentence that says, this sentence is a lie. Right? Is it a lie? This sentence is a lie. I'll do it with myself. I am a liar. Well, if I'm a liar, then what I just said is a lie. So I'm not a liar. Right?
Not all.
If I say I always lie, right? There you go. If I always lie, then I'm lying right now. Therefore, I don't always lie. Right? If I'm not a liar and I don't always lie, then this thing that I just said was the truth. Right? So it's all it all deals with self-reference, recursion, basically. Right? It turns out that if you have an algorithm or a problem, I should say. We know about algorithms that are recursive, right? You can just take any old recursive algorithm, an algorithm that calls itself, a function that calls itself. But what we're doing is we're going to formulate a problem that refers to itself. And it turns out when you do that, weird things happen. Right? If you've ever seen Russell's paradox on sets, that's why Zermelo-Frankel set theory is necessary, to put controls so that you don't have Russell's paradox. And you can't just say anything that you want about sets, right? Do you talk about that at all in 235? Okay, all right. That's unfortunate because one of the programming assignments that I give in 235 is how do programming languages deal with Russell's paradox. So basically, it's take a Java set, right, and add that set to itself. What happens? All right.
Well, doesn't it
So
just
here, I'll just show it to you. Well, I don't have a Java open right now, but suppose that we have a Java code here. Java. Oops, sorry, Java. And I'll take a set. I'm not going to parameterize it because parameterizations fix this stuff. Okay? So I'm just going to have a set S is equal to new set. Right? S.add A. Right. S.add B. And then S.add S. What happens?
why is that a problem?
Yeah, is it a problem? So, does S belong to itself or not? So, if you want to, we can take a digression on Friday and talk about Russell's paradox. But this is basically what happens when you don't have Zermelo-Frankel set theory. Can a set be a member of itself? Right? And it turns out to be it turns out to give you a paradox, right? Because you can formulate a set that doesn't belong to itself, or you can formulate all the sets that don't have themselves as members of themselves, and then that leads to a contradiction, right? You can come up with a statement that is both true and false at the same time, like I always lie. Well, if I always lie, then I'm contradicting myself, right? So, can you do this in Java, by the way? Try it. As long as you're using raw types like this, you can. Try printing it out. Try asking whether or not S is part of the set, right? If S dot contains S, system.out.println, how? Right?
So it allows me to create set without parameter.
If you parameterize this for strings, then you could not add something that was not a string. So that's the Java solution, one of Java's solutions for this. If I parameterize this so that it was only strings, now this becomes a compile error.
Wait, would you just say the statement that I always lie is just false?
I mean, in that particular answer, yes, because I think you could say that that one instance was a lie. said this statement is a lie.
Yeah. If this statement is false, or then, all right, well, if it's false, then it must be that this statement is true. Well, if the statement is true, the statement is that it's false, therefore it must be false. Right? You're going around in circles. How do you solve this? Well, you watch the movie Labyrinth, and you get two people, one that always tells the truth and one that always lies, and then you don't ask any questions that require self-reference. You ask a question that requires bidirectional reference. And you say, would he say that you always lie? Right? And then you can deduce from there who the liar is. Right? Nobody's ever seen that movie? No?
There's a lot of.
You need more Muppets in your life then. All right. All right. I'll see you on Friday then. Just